is equal to cos 2 pi 100x plus 250y. What are going to be the criteria for sampling such an image? The first criteria given for this is dx is given as 0.001 and dy is given as 0.001. So first, what we are interested in finding out, as from the previous problem, is that we would like to find out what is the sampling frequency, which is given by 1 by dx. So it is 1 by 0.001, which means it results in 1000. Same thing applies to fsy. So this also results in 1000. Next, we would like to know what is the maximum frequency in the x coordinate and in the y coordinate, thereby getting the value as 100 and 250. So we have got 100 and 250 here. We would like to just apply the Nyquist criteria, which states, just check whether the sampling frequency is greater than 2 fm, that is the basic 1D criteria. Coming to the 2D image, it is fsx is greater than 2x max. Similarly, fsy is greater than 2fy max. So considering this base, we have it is 1000 is greater than, this is 100, and here 1000 is greater than 250. So the solution is obtained, which means Nyquist criteria is satisfied. Thus, we see that we have got a case where the image is satisfying the Nyquist criteria. Let us go on for another example. Here, something similar to the composite signal that we had considered in 1D, we have tried to implement it. We have tried to create an image which has got cos with the one x component and a sine with another x component. Similarly, there is a cos with a y component as well as with another y component. So the sampling intervals are given as dx is equal to 0.01 and dy is equal to 0.01. So what happens is that the sampling frequency is going to be fsx is 1 by dx, this is 100. Similarly, this is fsy, this is 1 by dy, so this is going to be 100. So what is fs max? Please consider how you need to consider the fx max. Here it is 100, here it is 500. So 500 is the larger value, so fx max is 500. Similarly, 750 is f5 max. So now if we check whether the Nyquist criteria is satisfied, we see that the Nyquist criteria is not satisfied. The major reason being the value of dx is quite less compared to the previous case, which was 0.001, has now become 0.01. So naturally 100 is not equal to 500, and similarly we will see 100 is also not equal to 750. That is why Nyquist criteria is not satisfied, which means here both fx and fy conditions are not satisfied. We could also have other types of cases where dx and dy may be different values, which we say is not a uniform. Preferably, we prefer dx and dy to have same values. In this case, let us try to consider what is a continuous function. A continuous time function with a unit impulse is a function which is familiar to many of them, but to some of them it may be new, hence this has been defined. It actually means in the continuous time domain, an impulse function of infinite magnitude is actually present at t equal to 0. Similar to this expression, an expression would be obtained as delta t is equal to actually infinity, but we would write it as 1 at t equal to 0, and it is 0 at all other points of t. Similarly, in the discrete time sequence, we could see here that delta of n is going to have a value of a magnitude 1 at n equal to 0, and as has been shown here, at n equal to 1, 2, 3, and -1, -2, and -3 also, it is having 0 value. Now, what is a shifted impulse sequence? A basic impulse sequence tells us that the impulse is present only at t equal to 0 or at n equal to 0. However, we could have shifted impulse, which could be represented by delta t minus t naught, which means here impulse is present at the value t naught. Most of you must be aware that a shift of minus t naught tells us that there is a shift in the right hand side of the time axis, and if this expression was t plus t naught, we would have represented that T naught is going to be a function on the other side of the time axis. So with this base, we are going to just consider that here T naught is on the right hand side of the positive time axis because T naught is minus T naught, and as a result we have a value. T naught may be 1, it may be 2, 3, whatever may be the value. Similarly, it is 0 for all other values, which means that an impulse as such is a signal which has only one value at one particular time. So a similar case is also seen for a discrete case where instead of T naught, we represent it as K. This is the general format, and this particular value of K is given by a shift again on the right hand side of the time axis, which means since it is minus K, we have shifted it towards the right. On the other hand, if it was plus K, I mentioned that the shift would have been on the left hand side of the time. So with this base, we are just considering what would be an impulse train. Impulse train was introduced last class, and it was mentioned that it is delta t minus k into t naught. And what is such an impulse train? We would see that an impulse train of that type tells us that, please note this, k could be 0. That means impulse would be present here. K is 0 means it is only at delta t. It is the same impulse that we have considered there, which means an impulse is available only at t equal to 0. Next, what we are considering is, let k be equal to 1. If k is equal to 1, we have, it will be present at t naught because it is t minus t naught. So just now we have seen it is t minus t naught. So this will also be present if, because the actual expression tells us that summation. So the actual expression runs out as delta t minus 0 t naught, which means delta t plus delta t minus t naught plus delta t minus 2 t naught, etc. on the positive side of the time axis. Similarly, on the negative side of the time axis, we know that if k is going to be negative, which means if k is going to be minus 1, we would be having it as delta t plus t naught. Similarly, delta t plus 2 t naught, so on and so forth. This is what is the meaning of a impulse train, or it is called as train of impulses. Various terminologies are used to represent a series of impulses, or usually it is simply called as sum of shifted impulses. So if we have sum of impulses, which is called as the train of impulses as shown here, it is clear that this would be having, please note there are 3 dots on this side and 3 dots on this side because it tends towards infinity. So this is the basic of an impulse train, which is represented by a series of values which represent from 0 to infinity of t naught, but maybe it will converge to a finite value. Now what happens is that most of us are familiar that when we have an impulse train, we could use it for applying it for Fourier, and when it is used for applying it for Fourier, what happens is that only the Fourier transform has been given here. It is the Fourier transform of the impulse train is given by the expression omega naught into k k equal to minus infinity to plus infinity delta omega minus k omega naught, where omega naught is the fundamental frequency, just like t naught is the fundamental period. Most of you would recall that omega naught and t naught are related by the function omega naught is equal to 2 pi by t naught. So with this basic relationship between omega naught and t naught, this conversion has been done in the Fourier domain, and the same signal has been shown because for the interpretation of sampling in the frequency domain, this particular expression assumes a lot of significance. So we can see that here, as can be seen in the previous case, when k is equal to 0, we will have only one particular function which is going to be here. That value of the function will be omega naught into that function. So it is not going to be just 1. And same way at omega naught, that is when k equal to 1, we will be having omega minus omega naught, which means it will be shifted by a value of omega naught. When it is 2 omega naught, it will be shifted by 2 omega naught, so on and so forth. Again, we could see that this is also a sum of impulse train starting from minus infinity to plus infinity, though here it has been shown only from minus 2 omega naught to plus 2 omega naught. With this base, let us go on to consider how it could be implemented for sampling in the frequency domain. And in many places we would see this representation also. T0 is actually the time period or the sampling time which is given by Ts. The expression what we are going to consider is going to be, basically we will be having a train of impulses. Just now we have seen, instead of n we have represented it as k equal to minus infinity to plus infinity delta t minus k into, we had considered it as T0. Just now we have seen T0 is equivalent to Ts, so n is equivalent to k, so the expression is the same. Now what happens is that once we have such an expression, we would like to find out what would be its impact, and we would like to represent that pulse function by p of t, because p just represents it as pulse. It does not represent power as is in the usual case for signals. And most of us are familiar with f of omega is equal to minus infinity to plus infinity f of t e power minus j omega t dt. This is nothing but the Fourier expression, which means if a signal or a function, actually in this case it's a function, f of t is given in the time domain, we could convert it into the frequency domain by going in for this particular expression. And most of you would recall that this is the basic continuous Fourier transform expression. In order to avoid any complication with Fourier, only the basic continuous Fourier transform has been considered, though it is having some drawbacks, like the continuous case is a problem when we are going to consider the sampling aspect. So what happens is that the sample signal is basically the frequency component of the signal or the image into the periodic impulse. This is what is basically what is happening in the frequency domain. Most of you would also recall another fundamental, that a multiplication in the frequency domain is always preferred, which is actually a convolution in the time domain. And for this reason, in many cases, we prefer to go in for frequency domain wherever we have multiplication. Sampling is one such example. If we go on for a little bit deep into what has been considered there, it is the same thing. We have got the train of impulses delta t minus n into delta t. Instead of delta t, we could be using Ts, we could be using T0, any term that is representing the sampling interval. Then we have gone on to say what would be its representation in frequency domain. Please recall that the general representation in frequency domain is, it should have been expected as p of omega. P of u has been used because in the 2D domain, that is for image processing, just like x and y in the spatial domain, the frequency domain is likely to be represented by u and v. These are going to be the two parameters which are going to represent that. So as such, we have got 1 by delta t, which is equivalent to omega naught summation delta u minus n s. Only here the frequency is considered, that's why we don't have 2 pi into delta t. That is why here also, here instead of omega naught, we have considered only delta t. As has been mentioned here, fs is equal to 1 by delta t. So what should have been written here would have been fs into summation n delta u minus n omega s. If you just recall in the previous slide, it was represented as omega naught into delta omega minus omega k omega naught. The same thing has come back here. Only thing, instead of using the angular frequency, the sampling frequency has been used. This is basically the frequency domain interpretation of quantity sampling. What is this particular case? A basic signal has been given. Please recall that this is not a signal. Actually, it is the frequency spectrum of a signal. That is why it has been represented as x of omega. This x of omega, you would like to multiply it with p of omega. P of omega is equivalent to what we have just now seen as p of u, which means it is actually a periodic train of impulses which is represented either by p of u or p of omega. In the normal case, it will be actually represented by p of omega, and you know that by now the difference or the distance between each of the impulses is going to be omega naught. As such, we have got 0, omega naught, 2 omega naught, 3 omega naught, so on and so forth. Similarly, on the negative axis of time also, because generally when we consider the analysis of the frequency is considered between minus omega to plus omega, and just generalizing it as minus omega to plus omega, it could mean for any specific value of omega, which could be either the sampling frequency, the base frequency, whatever it is. The reason being, the Fourier is generally represented, it is two-sided. It is applicable both for the negative side as well as for the positive side, but in real-time case, we will be considering only the positive side of the frequency analysis. So what do we do? We are going to multiply these two. What is our requirement? As has been shown here, it has been mentioned here that Fs is greater than 2Fm, which means the distance here is greater than 2Fm. Let us go by a simple example. Let us assume omega naught to be a mere number instead of having this 2 pi and all, just to consider it as an example. So we may consider this as 50, and I would like to keep this as 200. If this is 200, we would be having this as, this is line till 50, this is line till minus 50. Similarly, here it will lie from minus 50 to plus 50. So we would see that the distance between these two is actually 200. So actually there would be a distance of around 100. So this is why we say that when Fs is quite larger than 2Fm, there is no chance of overlap. The next case that has been considered is Fs is less than 2Fm. We have considered a case where Fs is greater than 2Fm and Fs we have taken it to be 200, whereas this we have taken it as a value which is 50. So that was tallying for the first case where we have seen that there is no sampling. Now the sampling frequency is reduced, which means Fs, which is an equivalent of omega naught without the 2 pi component, is now reduced to, let us assume it is 75. If it is 75, you would see that there will be an overlapping because a signal from here would extend from 0 to plus 50 and here to minus 50. Here it is at 75, which means from 75 if you draw a line, it would extend into this particular region, which means it is going to start, or the negative part of the signal at 75 would actually start at 25, which means there is an overlap. Similarly, the ending of this 75 signal would be at 75 plus 50, which means it is at 125. Again, we have another signal here, which is going to be at 150. So at 150, when we see the signal, it will again extend here, which means this overlapping is what we call as the aliasing effect, or the basic sampling frequency violation, which results in output which would be represented generally by a DC line instead of having these values. And it was here that it was mentioned that higher frequency components will be appearing as lower frequency components, and lower frequency components will be appearing as higher frequency components. We will just go one step ahead, try to understand this expression, and then we will once more analyze the entire concept, then go on to apply it for images. So what happens in this particular case? We are already familiar with this expression that what is happening in sampling is we are multiplying the frequency spectrum of a signal with the frequency equivalent of an impulse given by this particular value, and that is what is obtained as the output. That is exactly what has been considered here. The only difference is, in order to introduce the 2D part, we need to consider what needs to be considered is, here we have considered that though there is m and n, it is only a n term which is available. So here we have x and y coordinate and two more coordinates, namely m and n. We have seen that they are components of the sampling frequency represented earlier as fs of m, n. So since they are components of sampling frequency, we will be getting that as x minus m into delta x, y minus n into delta y. And p into u of v, I mentioned just now that the frequency equivalent of an image would be represented by UV coordinates just like XY coordinates in the spatial domain. So this particular value turns out to be 1 by delta x into delta y, which would be given by the same expression replacing wherever we have delta x, we would be replacing fsx and fsy, just like here we are replacing it with fs. So with this particular base, we will just complete the expression to see what would be the sampling frequency expression. So considering this and multiplying the two values, we would be getting it as delta u minus m into fsx into v minus n fsy would result in, because this is just an impulse which is multiplied with an impulse fuv, it will just give you f into u minus m m fsx, similarly y minus fsy, where as usual fsx and fsy are equivalent to 1 by delta